Hello, I'm Greg Stitt. In this video, I'm going to continue talking about how to design AFUs for the Intel Platform Acceleration Card using RTL code. And the specific topic of this video will be how to do multi-cycle reads using memory mapped I/O. Just to remind you, I had an earlier presentation where I demonstrated how to do single cycle MMIO reads. And this is sufficient for the vast majority of use cases you will probably work with. So most circuits implemented in an FPGA will have some set of control status registers. Because they're registers, they can provide their value immediately, and so you can basically always respond in one cycle if all you have are registers. But that's not always the case. So for some applications, you are going to have resources that can be accessed over MMIO that require multi-cycle reads. So I have a few examples of this. Let's say you implemented a 2D convolution circuit. One of the inputs to convolution is the kernel or the set of filter coefficients. And that's usually only something that you have to load once, and then you process a bunch of images with that same filter. And so you don't really need the bandwidth from the other communication methods. So memory mapped I/O works fine there. But the issue is, if your kernel is large, you may not want to use a register or registers to implement the entire kernel, so you might want to use block RAM. But the problem is block RAM at a minimum requires one cycle of read latency, and if you register the output, which is frequently done to improve timing, then you have a 2-cycle latency. And if you have a 2-cycle latency, you obviously can't respond within the same cycle when a read occurs, and so you have to handle that read across multiple cycles. Another situation would be you have some circuit, it could be doing anything, and the output of that circuit is memory mapped so that you can read it over MMIO. Now, because that circuit could be executing in the middle of its execution when that read request occurs, you really don't know when the result's going to be available. So it's almost certainly not going to be available that cycle. It's going to require multiple cycles, and it may be non-deterministic. So there has to be ways of dealing with these situations, and that is what I'm going to show you in this set of slides. So the example that I'm using from the repository is this MMIO MC read. MC is for multi-cycle read, and the link to the example code on the repository is shown at the bottom of the slide. All right, here's a quick review of how memory mapped reads worked. I presented this in an earlier presentation where I talked about this core cache interface protocol and how you do memory mapped I/O reads and writes using that protocol. For a read, the basic idea is on channel C0 of the receive port, there's this MMIO read valid signal. When that gets asserted, that means the processor is trying to read something from the AFU. Now, in the same cycle that read valid is asserted, there's an address that is provided. So your AFU has to look up the resource that corresponds to that address and then provide the value back. At the same time, there is a transaction ID that is provided along with the address and the read valid signal. So now it doesn't really matter how long you take to respond. I'm sure there's a maximum. I don't know what it is. But the point here is that in the earlier presentation, I showed you how to implement a system that always responds within a single cycle. You don't have to do that, and that's what we're not going to do in this set of slides. Really, all we have to do is after some amount of time, after the read data is available, we put that on channel C2 of the transmit port. At the same time, we provide the corresponding transaction ID on the same C2 channel. There's this header.tid port. We put the value there of the transaction ID that we're responding to. And then we assert the MMIO read valid signal on channel C2 of the transmit port. So we can allow some amount of time to pass up to whatever the maximum is. I don't know what that is, but we're unlikely to hit it in these examples I'm going to show you. But we can wait some amount of time and then do this. So that's what we're going to see how to do in the next few slides. This slide here shows how we implemented the single cycle MMIO reads. Basically, we had some number of registers that were memory mapped. Here I'm calling them control status registers, or CSRs. Those went into a MUX to select the appropriate register based off of the address that was being requested. So we had some comparators, we had an encoder that formed the select of that mux. The output of that mux went to a register that provided the data on the transmit port. We then had other registers that just delayed the read valid signal by one cycle, and a register that delayed the transaction ID by one cycle. So if we need to respond in a single cycle, this is all we need. We basically need a few registers and some steering logic. And now we could conceptually add a block RAM to this mux to select between the registers or the block RAM. But in this example, I'm going to show you the block RAM has a 3-cycle read latency. Now this is somewhat synthetic. Normally a block RAM would have either a 1 or a 2-cycle read latency, which would still require the changes I'm going to show you, but I made it 3 just to make this example a little bit more obvious of what the problems are. So the problem is now when you have a 3-cycle read latency, if you use the exact circuit that is shown here, basically the address that is being used to create the select line for the mux sets that select before the data from the block RAM is available. Likewise, the transaction ID is going to be provided 2 cycles too early. It's going to pass through one register, which creates a cycle of delay, but our block RAM isn't going to provide the data until 2 cycles later. And similarly, we're going to basically assert the read valid signal on the transmit port 2 cycles too early because the data hasn't showed up yet. So we're going to be responding to a read request within a cycle, but we're going to be providing the wrong data. So we need to modify this circuit to work with a 3-cycle read latency of the block RAM. Fortunately, it's pretty easy to solve this problem. The basic strategy we are going to use here is we're going to delay all of the read response signals that we send on the transmit port by the same amount of time it takes to read from the block RAM. So if you look at the incoming address, we're going to delay that by 3 cycles because that's how long it takes to read from the block RAM in this example. That delayed address is then going to go into the comparator and figure out either which control status register we're trying to read from, or it's going to select from the block RAM. Same thing with the read valid signal. So we just take the incoming read valid signal, we delay it by 3 cycles. The output of that delay becomes the transmitted read valid signal. And the same thing with the transaction ID. So the transaction ID comes into the circuit, we delay it by 3 cycles, we then provide the same transaction ID on the transmit port, and we are now able to respond to everything with all of the data aligned with the control signals. Now, a few things you'll notice about this. You'll notice that there are no longer registers on all the transmit port signals. And that is intentional because the delays basically already have those registers as part of them. You could, of course, implement a delay using other resources, but typically it's done with registers. So I could have kept the figure the same and showed all of the transmit signals as a register, but then I would have to change the delays accordingly, and that's just kind of confusing. So I just showed basically what made the most sense to me, and this is also corresponds to how the code was written. So this schematic more closely matches what you will find in the actual RTL code. And the other thing I want to point out is that this strategy here will only work when there is a fixed latency. So you would basically take all of your resources that have been memory mapped, you take the one with the longest latency, and that is how you would delay things. Now, if you had block RAMs with different latencies for some weird reason, or just different types of resources with different latencies, you might have to add extra delays that are not being shown, but you would use this same basic strategy to align everything. Now, we still need a way of dealing with multi-cycle reads that have a variable latency. So the delay strategy we worked before doesn't work with a variable latency, or at least doesn't work easily with a variable latency. So there's a lot of things we can do. One potential thing we could do is we handle read responses in a similar way, and when a resource provides its read data, we write that into a FIFO. So registers could write into that FIFO in the same cycle, block RAMs would write to it in one or several cycles, and then other resources that have a variable amount of latency would just write to the FIFO whenever the data is available. And then the read response that you put on the transmit port, it would simply just read the transaction ID and this corresponding data from the FIFO whenever it wasn't empty. So that would be very simple control. Now, there's a challenge with this though, because of the different timings between each type of resource. You may have conflicts, write conflicts for the FIFO. For example, if you have a blockgram read request that happens at one cycle, and then 2 cycles later, you have a read request for a register, it's possible for both of those resources, the register and the blockram, to want to provide their data to the write port of this FIFO at the same time. That's obviously not possible. So if you want to use this strategy, the real challenge is you have to have some form of arbitration. And that can be a little bit tricky because you have to basically preserve the information about the read request until everything has actually been written into the FIFO. So an alternative strategy that you could use when dealing with variable latency resources is to buffer all incoming MMIO read requests. So as soon as a read request appears, you basically store it into a FIFO. We're then going to handle all of the requests in the order that they arrive by essentially having a simple controller that whenever the buffer isn't empty, we're going to just pop the first request out of the buffer. We're then going to do all the same decoding logic and steering logic that we did before and just simply wait until that data becomes available. If it's a register, it'll be available immediately. If it's a block RAM, it'll be available in 1 or several cycles. Or if it's something else, we wait until it just happens to be ready. Once the data is ready, we provide the same read response like we did before, and then we go back and pop the next read request off the FIFO and so on. So this is a much easier way of implementing things because you don't have to worry about any kind of conflicts, but it does have some limitations. So one problem is if read requests come into the AFU faster than you are servicing them, then this buffer is going to overflow and read requests are just going to be lost. Obviously that's bad. The good news is that's unlikely to occur, at least on the Intel PAC, because all of this MMIO is done over PCI Express. So your memory mapped resources would really have to take a long time to provide their data for this input FIFO to overflow. All right, just to summarize, in this presentation, I demonstrated various strategies for multi-cycle MMIO reads. I talked about a fixed latency strategy where we simply delayed the read response until we had all of the data that we needed. I then talked about several variable latency approaches where we basically used FIFOs to wait different amounts of time. And I just want to remind you that there is a code example on the repository that demonstrates the fixed latency example that I talked about on these slides.